Log on, tune in, find out. Another good idea from Cambridge.
For the, in some sense, third talk of the day, we have Martin Cederwall, who will be talking to us about U-duality things?
Yeah.
U-duality things, thank you.
So I'm going to tell you some things about work that is in progress, in very early progress, I would say. So some parts it's some ideas about how to do things. I've checked a couple of things and I would be very happy for any input. So what I'm interested in basically here is to do U-duality and supersymmetry at the same time. How do I manifest, if possible, well, certainly possible, both U-duality and supersymmetry in an as efficient way as possible? I don't know the answer, but I have some ideas. I've been working for some years, mostly now with pure spinor formulations of supersymmetric theories, essentially maximally supersymmetric, because that's where the pure spinor formalism is most powerful. And as you know, perhaps, pure spinor is one way, to me, the most natural way to make maximal supersymmetry, to do maximal supersymmetry off shell. Is this well known to everybody? Otherwise I might say some words about it, actually. I'm willing to adapt.
I can't speak very well.
There's a long history about supermultiplets and superfield formulations. Normally what happens when you start to increase the number of supersymmetries, a superfield will contain many components, which is maybe fine because you can eliminate them in various ways. But what happens when you have maximal supersymmetry and you try to eliminate the field to get down to an ordinary supermultiplet, turns out that that will give you the equations of motion for your superfields, for your component fields.
It was
right?
only about maximally supersymmetric theories.
Sorry?
Four young mills, semi-prosaic superreality.
Yes?
But you can't make an offshore, field spinners don't need an offshore formulation.
Why are you saying this?
Well, I'm just asking a question, but
This is exactly what it does.
It does, because
Yeah.
I thought, okay, well, I should have known that.
So the pure spinor formalism, in a way, it solves this in a very traditional way, I would say, because the equations of motion in the pure spinor formalism can be, roughly speaking, identified with exactly those constraints you would want to put on the superfield in order to imply the equations of motion. What is usually called, some of them are called conventional constraints, but some are the ones that really do this. If
You need an infinite number of auxiliary fields.
Absolutely,
So
but they have.
superspace, you get.
But they have.
You get the 3, n equals 3. So
Let me say a couple of words about this, because I think this is an important point. If it wasn't for this, I wouldn't be sort of interested in doing it at all. Well, I could do ordinary superspace. Let me say a few words about the simplest case, which is super young mills. 10 dimensions, to make it as easy as possible, okay? Or should I skip this?
No, that's good.
Paul needs it. Yeah, okay. So there's a bit of propaganda then for the pure spinor formalism. So I won't do everything for you. I will sketch a lot of things. So what you do in one way, or the natural way of doing supersymmetric Yang-Mills in superspace is to do it as Yang-Mills on superspace, right? Which means that you have connection, which has both bosonic and fermionic, contains forms. So let me denote them as follows. So this is bosonic index, this is fermionic index, so it's one form on the full fermionic. This is funny notation which is sometimes used, but I don't want to use curved fermionic indices, so let me flatten those with suitable field binds so they become Lorentz vector and a spinner. I can't call the fermionic part a spinner unless I make it flat, that's what, right. So you won't ever see that again. And both depend on x and theta. 10x is 16 thetas, chiral superspace. So these are superfields, incredible amount of component fields in here, clearly much too many. And one important observation is that this superfield is in practice not needed. This is enough. So why? Well, because if I take one fermionic derivative of that one, that would give me, well, at least one component which is a vector, which has the correct dimension, etc. So I don't want two, so I could say that, well, this is A. This is, to identify it that way, means that's called a conventional constraint. Now, the chalks are very small, okay. That's called a conventional constraint. So how do there's a better way of saying this, which is more covariant, because I don't want to impose constraints on connections, right? So what I want to say is f alpha beta equals 0, because that's just one derivative on A, but not all maybe. I contracted with the gamma matrix. So this is a conventional constraint. Doesn't do much. Well, it takes this away and leaves me with that. Then what you can do in order to get on shell is to think about what about the rest of this field strength? Well, the field strength of A has dimension 2. The fermions have dimension 3/2, inverse length dimension. There is nothing really at dimension 1 where this sits. There's nothing physical that fit in, which is covariant. I mean, there's a connection, but I can't use that. So the whole field strength should really go away, at least on shell, I hope. So even the other part of this constraint. Now, bispinor symmetric goes into a vector and self-dual 5 form in 10 dimensions. So I try that too, but that's the physical one. And I won't do the calculation, but everything is on shell. So it turns out I get this one, fulfills the equations of motion, I get the fermions. So that's a traditional superspace formulation, minus the calculations, which are not that difficult. That's very old. And this is why you say that when you try to, you can't find a linear multiplet off shell, not a finite number auxiliary fields which helps you to write an action, etc. Of course, you could stay with that one and say, well, that's my off-shell field, and in a sense it is. But then so what the pure spinor formalism does, I'll try to be a little quick here, is that you introduce in addition to x and theta, you introduce a bosonic spinor. Strange statistics, but it's because it's a ghost field. It's allowed to have the opposite statistics. And then you see how expand this in ordinary superfields. Excuse me the funny names, but I just choose something. Power expansion in this spinor. Now, this spinor is assumed to be pure, and I'll show you why this is meaningful in a little moment, why this is exactly what is needed. So lambda is pure, meaning that in 10 dimensions, are different ways of defining pure spinors. This is not a universal form. I mean, you can't even, in some dimensions, you can't even form this, but in 10 dimensions, this corresponds exactly to the traditional way of defining a pure spinor, in the sense that this goes away, and what is left is the 5 form, the half. Yes?
What's the dimensionally independent definition? That's annihilated by a certain...
It's annihilated by a number of gamma matrices, which is half the dimension. And such a subspace spanned by the gamma matrices, it's annihilated by, it's always an isotropic subspace. Now, which means light-like. Now,
So
SO1.
half the dimension in 10 dimensions.
Sorry?
Half the dimension in 10.
It's 5.
10 is 5.
Yes. You don't have light-like 5 planes in 1,9, which means that this has to be complex. That's
But
fine.
you're not. It sounded like you were saying the opposite of the way around. You're the 5 and the one you're not annihilating. You're not saying it's annihilated by 5. You're not.
No,
it sounded
no,
like
no,
what you
no,
said
no.
in words, that I should
No, no.
have a lambda with the 5 gammas,
No.
lambda is equal to 0.
No,
It was actually the other one.
that's non-zero.
Yeah.
But in principle, I mean, barring signature, I mean, you can divide in plus and minus directions. So, and this means that, for example, gamma is annihilated by these 5 gamma matrices, but not by these.
Lambda, you mean lambda? Is
Sorry, lambda, yeah. But when you wedge it 2 lambdas and then acting left or right,
I
it sort of
see.
transform plus to minus, so that,
I see.
Yeah.
I see. That
So that
would
will
be
give
yeah.
So
Right.
lambda will be real in SO55.
yes, it is. Yeah. Okay, so why do I do this? Well, because this makes it possible for me to define a BRST operator like this, a covariant derivative. Namely because there's a torsion on flat superspace. Well, I don't care about numbers here. So the torsion is a gamma matrix. So if I check the square of this, there would be just this anti-commutator, but the pure spinor constraint will take it away. So that means that I have a complex, I have a nilpotent operator, and I can talk about cohomology. So why is this related to what I said before? Well, see what happens when I go from here to here with Q. I pick up a lambda, and I take the fermionic part of the exterior covariant derivative, so to say, acting on A. So I get this. Let's not talk. Let's think linear. VRST is linear. So not Maxwell theory for the moment. Then I can do interactions. So what I get from cube psi equals 0 is exactly this. This one is completely irrelevant. I mean, I don't care about it because there's no, I don't need a conventional constraint. I don't have it even introduced the vector part of the connection from the beginning. So that's fine. And the Q from here to here means just gauge transformation. So cohomology, exact solutions. I know this corresponds to the component equations in motion. Modulo gauge transformation. So cohomology, physical fields are given by cohomology. So this is this part, but there is other cohomology too. Actually, if you want to calculate the cohomology, there's a sort of natural two-step way of doing it. First, you just do it for zero modes with respect to x. Why? Well, because then I have just d theta. It's just a purely algebraic calculation. It will give me full representations of the Lorentz group, and since d dx is thrown away, I can't get any equations in motion. So that will give me the off-shell fields. Then if I reintroduce the x dependence, the cohomology here will tell me where the derivatives on these fields can possibly land. So this will tell me cohomology here will tell me equations in motion. Right, like cohomology here tells me, or zero mode cohomology here tells me what is the gauge symmetry. So here is just a singlet, the x and theta independent, theta independent part of this one. Well, that's not really gauge transformations because it has the wrong statistics, but it's a ghost. So here ghosts, fields, and if I read off cohomology here, it's like equations in motion, but they are again wrong statistics. So it's anti-fields in the Battalion-Wilkowiski sense. And I actually find, if I check that zero-mode cohomology, I would find the ghost, I would find the vector of the spinner. Here I will find the corresponding vector and spinner for the equations of motion, all at correct, up in the theta expansion. And here I will find one singlet up at order theta to the fifth, actually. And this is the anti-field for the ghost. So this points very much to Battalion-Wilkowiski formalism. And it's what it is. So what remains now, if I want to go to really claim that this is an off-shell formulation, I will need to write down an action, right? Otherwise, it doesn't count. And I know what happened. Something. I know what the equations of motion for that action should be. It should be this, or maybe with some interaction terms. So this is, I mean, it all got, this whole procedure sort of starts from traditional superspace formalism, discovers a structure in there, cohomology, etc., and builds on that. So I really need to, so if I want to, that's called all coordinates z together, I need to find a way to integrate and to write an action of type psi cube psi. And if I want to introduce that interactions, well, maybe something like this. Psi is fermionic, clearly. It also has ghost number 1, starts with a ghost, gauge symmetry. So this has to have ghost number, integration has ghost number -3. I won't tell you all the details about that. Roughly speaking, you can sort of find a candidate for integration which is wrong but almost right, which is a kind of residue where you pick out the position here at lambda cube theta to the 5th where the last cohomology sits. Well, then there is no more cohomology, by the way. That's all. And pick out that component as a residue. Clearly has ghost number -3 because it takes away 3 lambdas. But it's not a true residue because you just have an expansion one way and not the other. So it's not, well, it's very degenerate. So it won't, it doesn't give you the full equations of motion. So it's not good. So you need a way to make that a similar integration, non-degenerate. And that can be done. That was done by Nathan Berkowitz well, a couple of years ago. And then you're home.
So I shouldn't feel so silly that I didn't know that. It's only 2 years ago.
No.
I've been busy.
Yeah. That was, I think, in
because
2005.
Because there's using harmonic superspace, there was a n equals, there was a Chern-Simons formulation of n equals 3 goes way back. We did it now, but running the Russians.
Yeah, Russian.
But this is you say for n equals 4. So
this is for n equals 4. I mean, I'm sketching it in 10 dimensions, but any dimensional reduction sort of trivially follows. I mean, 4 dimensions is fine. Same pure spinner. So there are several interesting things I think about these formulations. You can, in a way, this. Had I tried to do this for a non-maximal theory, I would get something, but clearly I wouldn't go on shell for the physical fields. And if I tried to calculate cohomologies for in such situations, what would happen is I will get something here, and then it stops. That's the last one. So it's sort of logical. Which means that the anti-fields sit in a separate field, and well, that's not very elegant. So in a way, this what used to be a problem is now a very good thing about the formulation. Fields, anti-fields, all in the same scalar field.
This superspace measure does measure on x, theta, and lambda.
Yeah.
So can you do the integrals over the thetas, and can you end up with can you express it ultimately as an infinite number of auxiliary fields? Is that the ordinary? I mean, can you express it ultimately in principle?
In principle, I mean,
as an ordinary integral, then an infinite number of auxiliary fields.
Yes, in principle, because I have the bosonic lambdas. There's some tricks involved in this, which are maybe more than tricks. I mean, but I have a lambda which is complex, so I have to.
Because of course, there were the no-go theorems always assumed a finite number of auxiliary fields.
Yeah.
So if you have an infinite number.
I'll tell you a little bit of what you have to do. You have to integrate over this complex space of pure spinors. You have to consider also lambda bar. But in order that not to change the homology, you introduce it together with a fermionic companion and their derivatives as a trivial quartet, which doesn't change the cohomology. You can always find a representative which is independent of those. Then you can integrate just over this cone as you want to do. And
I remember now, I've heard
yeah.
Nathan talk on this.
Yeah.
I seem to remember being...
An even more elegant way of saying this is that this fermion is d lambda bar, and then psi becomes a cochain, a holomorphic anti-holomorphic cochain, and the measure becomes very simple and geometric, and works because this space is Calabi-Yau, non-compact Calabi-Yau space, etc. But I mean, it's all very nice. Yeah, one observation here is that, I mean, this is Chern-Simons thing. The cubic interaction is in Yang-Mills, super Yang-Mills, it's sort of the essential one. The quartic one comes from eliminating fields and doing the equations of motion twice, or by sort of doing this with some trivially propagating field in between, which sort of has a point-like propagator. Similar things happen also in other theories, and let me say I wouldn't want to start out with U-duality if I didn't know that this worked for supergravity. So in supergravity in 11 dimensions, you also have a similar description. A scalar field, everything sits in a scalar field. Beautiful. So what do I call this? Now, you know what about the gauge symmetries there is a 3-form which has a 2-form, so there's a 2-form ghost, but it's reducible, so you get ghost for ghost and ghost for ghost for ghost, and finally you're down at 1. So it starts out with the field here has ghost number 3, and then at lambda cube comes what is the lowest dimensional component of the superspace in the superspace formulation of the 3-form of the supergravity, and this is the basic field. So if you check this cohomology, before you do that, you will need to know what spinors look like and how to define a pure spinor, which you normally don't do. I mean, not the traditional way, but this has been discussed long ago. I mean, people have tried different things. So what you actually need to do here is exactly the same thing. Now it's odd dimension. I can't define it as easily by saying isotropic half-dimensional spaces, right? And what remains here is not just one, but a reducible representation. 2 forms and 5 forms. I wouldn't know a priori why. I mean, this has to go away because of the torsion. Right. So in that sense, this is natural. Why this can't go away because it's the biggest one that will kill the spinor altogether. It's possible to make this, to take this to 0, but that doesn't give you any sensible fields, cohomologies. Paul Howe was playing with this many years ago, and he sometimes, I think, used also this. If you set also this to 0, it becomes equivalent to, as you clearly see, to a pure spinor in 12 dimensions. So that's something else. So you calculate the cohomology and you find, wow, all the supergravity fields come out. Cohomology is corresponding to the correct ghosts. I mean, these are the superfields. They tend to come sort of further and further up. You get the physical fields, anti-fields, and there's this symmetric structure in the cohomology. Yes?
So would the action again be Chern-Simons? I mean, psi q psi plus psi squared. Q.
Well, that's the problem. So you can write psi cube psi, which is fine if you, let me do this. Now psi has ghost number 3, so this has to have ghost number -7. And in fact, if you think, I mean, go through the number of fields and anti-fields and actually check that they are in your cohomology, you find that the anti-field of this sits at lambda to the 7th power and theta to whatever, 9, I think. So yes.
So you have 32 components then?
32 components. And this constraint leaves 23. It's always, I mean, here 16 goes to 11. It's not the 10 you might think. This always happens. Here there is also some reducibility, but not as big. If I also say that, it takes me down to 16. Which is well known from Hitchin's generalized complex geometry things.
Can you, if you compactify on a circle and down 10 dimensions, can you see how the 10 dimensional string, rather, 10 dimensions,
No.
n equals 250?
Yeah, I mean, I can sort of trivially get the supergravity out. Yes.
With the action. I mean,
Yes. I mean, yes. But I don't get the ordinary pure spinor formulation of the superstring because that builds on, I mean, left and right moving, two sets of pure spinors. So that would be very difficult to write a field theory with that zero mode, that from that. I don't know how to do that.
The left and right-handed pieces of the spinor.
Yes, I would need two Q's and the equation of motion that enforces both. I don't know how to do that.
That's why I was.
So I don't know. And the relation between 11-dimensional pure spinors and 10-dimensional pure spinors is very tricky. I don't understand it. Probably because of this. They aren't really related. So if I want to introduce interactions here, I mean, this has ghost number 3. I can't have psi cube. On the other hand, what you know is that there is another way of maybe the way of getting the interacting supergravity in superspace. That's just to start from field lines, torsions, connections, blah blah blah. Cut-on formulation. Impose some constraints, which eventually turn out to mean that that the only relevant field flattened is this one, and then do the geometry in a covariant way, and you will find out all the fields. So this indicates that there should be another field, another pure spinor field, which is phi a, which is some Ca plus lambda alpha E alpha a plus blah blah blah. And there is. And you can check the cohomology for this one, and you find the supergravity fields again. However, since the gauge structure here is only diffeomorphisms, well, actually, next order in theta, you get, of course, you get local supersymmetries, but you never see in this geometric picture of the supergravity, you never see C, the 3-4, you see H. So So you can't use this one to build an action for this simple reason. You never get the CYH, which Simon's term can't come out. So, and you can check the cohomology. I mean, everything's fine, but so the Bianchi identity here instead is enforced via equations of motion, which come in the cohomology at the next level. So maybe something, what I thought, I should also mention that this one, so you might ask me, why if I just hang on an index, what happens to the cohomology? Well, nothing. Obviously, since Q is scalar, the cohomology would just multiply the old cohomology with that representation of the Lorentz group. That's just stupid. So I don't want to do that. I have to do something which mixes with this index. So what I say is also that in addition to the pure spinor constraints, I have another invariance, and that is that I shift, I form an equivalence class. Pure spinor constraint can be seen as taking equivalence classes, divided out by some ideal of functions generated by. Here I form another equivalence class that I also divide out by lambda, gamma A, anything, any function of anything. So this sort of effectively brings down the number of representations. It also mixes in lambda with this index, so I get something completely different. But this means that I can't write a naked phi because it won't respect this. What I can write is this. Because if I do this, this is not the standard 11-dimensional Firth identity, but it's almost. It's a Firth identity for pure spinors. But if I put that there, this goes to 0. Yeah?
Can I ask a slightly different question? Paul already mentioned the counting theorems that were against having offshore formulations. It's not that I doubt anything of what you're saying, but I just want to see what his argument would go. I mean, there is one argument if you want to, that starts from the supersymmetry algebra. And if you want to have an offshore formulation, then it means that if you want to make a superderivative, for instance, but it's the same argument for the angles, you want to have a massive representation of the supersymmetry algebra. And that's basically the first reason why offshore representations go wrong for extended superderivative, if the extension is high enough. Because when you pass n equal to 4, a massive multiplet has necessarily spins, fields with spin higher than 2. Now this is assuming, of course, that, well, you make the representation with the standard supersymmetry algebra, you assume that there are no central charges, and so on and so forth. You have any idea how, at that level, you understand why the spinor formalism can sort of avoid this?
I think it avoids it essentially because it is it introduces fields. I mean, I could say that this A alpha completely unconstrained is my off-shell multiplet. Of course, any unconstrained field is okay, but then I can't use just this. I have to introduce fields with other ghost numbers. I have to go to Batali-Minkowski framework. I think that is what really evades those arguments.
I mean, you also break Lorentz invariance, of course.
No.
I mean, your lambda is different from 0, so.
No, it's not a fixed spinor. It's a variable, which is defined in the Lorentz covariant way.
Yeah, but surely, if I think in terms of the standard supersymmetry algebra, I have no knowledge of lambda. So, from that perspective, it looks like I'm violating Lorentz invariance. I mean, at the algebraic level of the supersymmetry algebra, something has to happen that will forbid me to make this argument.
Yes, I'm not sure. I can't tell. I'm not sure. But I suspect it has to do with this, maybe this. Of course, it's an infinite number of fields.
Yeah, I understand that.
So back to this, I mean, to interactions, it turns out that what I can write down is actually, I would like, from the fact that I have C here and the H here, I might like 2 psi's and 2 of these. So I could write something like lambda gamma AB, lambda psi, phi I, phi B. Turns out to have the correct ghost number, 1 plus 1 plus 3 plus 1 plus 1 is 7. These are there because of ghost number, they are there because this is not invariant under that transformation otherwise. They are there because I need something anti-symmetric to contract these fermionic phi's with, etc. I mean, they're there for all reasons. So that means. Then, of course, this is not fine before I can say that this is some operator can form this from that, because this is a fundamental field containing everything. And once I found that, it's nice. And I know this operator. I won't tell you what it looks like. I mean, it's just an operator. That steps around, takes away some lambdas, put in some derivatives, blah blah.
So it is cubic in the psi at the end. Yeah.
It's cubic. If I just continue this, there is actually a quartic term too, but I can take that away by a field redefinition. So I get something little here in front on this. So it's a polynomial action for 11-dimensional supergravity.
So you're adding that to the thing.
Yes.
First term is
Yeah. That's a plus.
Yeah, so to reiterate what Paul said, it's cubic still in psi, but with a whole bunch of, in some sense, projection. I mean, with the lambdas and the R and the rest
So it's difficult to see where background invariance is. Gauge invariance is sort of manifestly there because I have all the right ghosts, etc. But geometry is somewhat obscured, I would say. So I wanted to take this and sort of move on. I've been playing this game for a while. You can do it for 3-dimensional conformal models, for example, BLG and ABJM, and what everything's simple. It's always becomes lower order. Instead of 6-point couplings for the scalars, conformal scalars, you get essentially minimal coupling. And then you have to apply equations of motion several times in order to generate that 6-scalar coupling. So I think this works nice. I was sort of interested in applying this to a setting where the symmetry group is different, and I was thinking about U-duality. So in a generalized geometric setting, you have more coordinates because you have all charges corresponding to winding membranes, fibranes, and maybe even more complicated things in the end will go together with momentum and form a multiplet under U-duality. So I wondered what will happen if I would try to play the same game, which initially is just algebra, checking for zero-mode cohomologies if the multiplets make sense. So I won't write down this table for you. I mean, maybe, well, I just mention a couple of observations I made about this. So you have of course a U-duality group, ENN I should say. EN. Does this mean I have to stop?
No, that means they're having coffee.
And I can't have any. Okay. Which you know by heart, so I won't write them down. I'll write an empty table for you. So, but since I want to do maximal supersymmetry, I mean, I can't just do this because I have to keep the uncompactified directions also. So there's some GL or whatever you like to call it. So the uncompactified symmetry. Now, of course, since I'm doing spinners, the representations I look at, I mean, will be a representation of the compact subgroup, the local subgroup. So what I will have is SOM plus the compact subalgebra of EM. So to take some example, I mean, say in 6 dimensions, n equals 6, I will have an SO1.
N is what? It's the dimension?
N is dimension of the torus. Yeah, so I will have 5 left, and I will have the compact subgroup of E6, 6, which is USP8.
It's 11 minus m in the
Yeah. Sorry. Thank you. 11 minus m. Yeah. Etc. So in order to decide what I want to check, I need 2 pieces of information. I need a spinner representation, and I need the constraints I want to put on the spinner. And then I need another piece of information, which is the representation in which I want to put the field. So I need to know the vector representation. Now I know what a vector representation is, of course. I mean, you can just read it in a table or figure out for yourself. The vector representation is 5, and for the transfers, and there's a 27 for this, which contains the 6 compact directions plus number of charges, or coordinates conjugate to charges. So this is what I want for a vector. But it's not obvious, as I told you about in the case of 11-dimensional supergravity, it's not obvious that this is exactly the constraint I want to put on the spinner bilinear. There could be, if I want to do supergravity, just supergravity, no dependence on internal coordinates, could be just that. Could be this, could even be more, because it doesn't hurt to take away more if it fits your purposes. So, I mean, you really have to check that you get something meaningful. Now it turns out, I think, that in all cases this choice is the natural one. This is not trivial. I mean, it could be that that was the good constraint, and I'm not allowed to put that constraint on a spinner. Then I should quit this immediately, and it will not work. But I am allowed, and it will generate some cohomologies that at least look like they contain the right thing. And then, of course, you need to say what your spinner is. I mean, this is well known, of course. There's 32 components, not much to choose between. It's a 4 with respect to the uncompactified, 8, and 8 of USP8. And you can do this for most of the cases. I'm not so sure about n equals 8 though. But if you do this, you get a nice sequence of pure spinners. So let me check. So the number of pure spinner constraints, these in general, of course, not spinners, they are representations of some funny groups. But the number of constraints is 8 minus n. That's a nice sequence. I mean, this, I think, if it's just some arbitrary numbers, I wouldn't believe I was. But then you need to find cohomology, check what kind of fields you have. And I would...
Probably you're writing the second column, top one. At the top.
SO 11 minus n. Which means that I have, what I have left is 24, 24 plus 8 plus, should be 8 plus n, should it? Yes, 8 plus n constraints. More and more constraints as I go down. Yeah.
So what's that number you just wrote? 24 plus n?
24 minus
Can't see
n.
the bottom of the board.
That's the number of constraints.
And that's the number left over.
Number of independence. There's a dimensionality of that space. They're always complex, of course. So then I have to look for cohomology. And
So can you just raise that board up a little bit because it's quite hard to see.
of course. And then I can even use this one.
So just to understand, starting with the 11 dimension n equals, oh, you started n equals 3.
Yes.
About n equals 0? That was,
So-
you said
so
22.
that's
You
a-
get 23 then, right?
That's an observation. This is not a sequence that contains uncompactified 11-dimensional supergravity for some reason. That was a little bit disappointing, but it's a fact. I cannot seem to be able to come up with any other constraints that where the end point of my sequence is ordinary 11 dimensions. No.
So you haven't mentioned duality yet,
Duality?
That's ENN.
That's the ENN.
Oh, yeah, but I mean, I missed a jump somewhere. These pure spinners,
They come in a representation of the compact
right,
subgroup.
Of the duality
Cover
group.
Of the duality group.
the full duality group.
Because spinors, I mean, fermions transform in the compact.
I know, I understand that, but I mean, you haven't yet told us.
What the fields are.
Yeah.
No? I haven't. What I expect here is if I do this right and I just look at zero mode cohomology, I will get something which can be interpreted as long as I don't turn on the extra fields. Should be possible to interpret it as an ordinary linearized supergravity. The cohomology is linearized, of course. So if I just turn on the uncompactified directions, dependence on those, this should generate a meaningful known set of supergravities, right? I guess so. Otherwise it would be very strange. But in this formalism, I have automatically the option of also turning on the internal directions, because it can't go wrong. It can't go wrong because I have the pure spinor constraint. So here, now let me now, before I stop in a couple of minutes, say a number of things I observed here, and it was not clear to me because
Perhaps, Martin, before you do that, so we're really clear about this table, I just want to be, you have here your EN, which is your U-duality group corresponding to dimension reduction on Tn.
yeah.
You then want to form pure spinners, which means you have in some notion of a spinner corresponding to that group, which is some sum of
It's the
forms.
same representation as the supersymmetries
Right.
come in.
Right, exactly. Okay. And then you have a pure spinor constraint on those things. And then you say from those pure spinners, you can write down an action, or one hopes.
No. I
But
won't be
you're
able. I won't be able to write down that.
You know, but you can at least,
I'll
now you're going to
copy
write
that.
down cohomologies.
Yeah, I can
Because
play with cohomologies. Yes.
Equations of motion should
Mm.
correspond to supergravities that will then have U-duality in some sense built in because they're made out of U-duality representations.
Yes. Yeah. That's the idea. So the way you guess the field is always, I mean, is there gauge symmetry? Okay, then I mean take the lowest ghost, and that's where you put your field. That's the way, because it's a Battalion-Minkowski framework or it's BRST. I mean, all those fields, all the ghost structure should come into cohomology. So you use the gauge symmetry to guess. Now I don't know enough about gauge symmetries in generalized geometry. They are sort of tricky and they are restricted to subspaces of this big space, probably because of a section condition. And I don't know how to incorporate that in this formalism. That might be a drawback, actually. It may turn out to be a drawback. So what I did was I tried a scalar field for some reason. I don't know why, just for fun, see what happens. I couldn't really find the right fields in it. I mean, lots of nice representations, and not too many, but I don't understand what it is. So then I tried various vectors, for example this, which is just the uncompactified things. I also tried vectors under the actual E groups. That just gave me nonsense. Maybe because of what I just said, section conditions, etc. So this was where I could find meaningful information. So I just list a little what I get here. So the ghosts I get here is the diffeomorphism come out. I mean, obviously, because I begin with that one. The super diffeomorphisms come out, right? And I also get the adjoint of the compact subgroup, which I think is nice, maybe if you want to consider gauged things. So that's in the ghost sector. So that looks nice to me. I would have been incredibly happy to see some generalized diffeomorphisms or things like that, but I don't. And I think this may have to do with section conditions and things like that, which I understand a little bit better since a couple of days than I did when I tried this. And I get fields which include graviton, I mean the correct representation. I get nice fermions, including gravitino, and then I get at dimension 1, I get some field strengths, often quite many, but including, because I mean they can appear as this, I mean uncompactified or compactified derivatives on some potential, and then so here there's a sort of a list in each case, and in the equations of motion also a list including the Bianchi identities, hopefully. Yeah, it has to be. So here is roughly speaking where I am right now. I notice that, well, some of the equations of motion are nice. I can see the equations of motion for the scalar fields, etc. And I know it's a gravitational theory. I know it has at least the compact part of U-duality group as a symmetry. I haven't yet been able to analyze, and I really would like to do this in some specific case, the linearized equations of motion properly and see what happens when I turn on the internal coordinates. That would be really exciting. There are several possible things that can happen, I think. One is that I get some equations of motion, and this is really the generalized geometry thing I should have. But I think most likely I will get, if I turn on all dependence, I will get much too strong conditions and everything will be zero, unless I put in some section condition. So I hope to see the section condition in here, in the equations of motion. That would be really nice, I think. But I haven't done that yet. What is a bit disappointing also is that these fields are not of the kind that allows you to write an action. In order to write an action, oh, you have little, one, okay. In order to write an action, you need a cohomology of some kind where you have a singlet at the end, because that you can sort of use as a measure, roughly speaking, in the residue sense I told you, and then make it non-degenerate by introduction of the non-minimal variables lambda bar and r. These cohomologies are not of that kind. There are other cohomologies so the ones that I find meaningful, and I don't know why, I just say it, let's see if it rings any bell. Fields where I have symmetrized traceless combinations of vector indices work nice up to some, so say I have, say in n compactified dimensions, I will have I don't remember the number, sorry. So I have a sequence of cohomologies. This is the one I really want to look at. Up to a certain number, all symmetric and traceless. And then it turns out that this highest one, I can't tell you what p is, maybe 10 minus n or something like that. This one looks like this one, but turned inside out. The cohomologies I showed you before look the same turned inside out. They have a certain symmetry between fields and antifields. This looks like an antifield to this one, and this one to this one, etc. But if I introduce that one to act as a Lagrange multiplier in front of q times this one, well, so I don't know. It doesn't look like I can write down an action. That, of course, doesn't stop me from thinking about interactions, which I really haven't done in a serious way yet. Okay, thank you.
Any questions? Go on, Axel.
Maybe just to check, so you said in the next step you find the antifields or the equations of motion, you see the Bianchi identities, do you also see the Einstein equation in there, linearized? Or?
The Einstein equation is there, absolutely. And I haven't checked. Normally I mean, you split in all this, so I can't say that in any specific case I've checked that this exactly matches all the field strength I want to have, but this could be reasonably easily done. And all the ones that I look for are there. So I mean, these are. I mean, if you just take away the dependence on the internal coordinates, I think this is a supergravity simply. But it's manifestly covariant, linearized, and supersymmetric. So what I really want to see was where things go when I turn on the internal derivatives.
Any more questions?
Hmm?
Does this work? I mean, you mentioned briefly not, maybe including 8 or not including 8.
I don't know. There's increasing number of constraints when I go down tends to make the cohomologies sort of narrower and deeper. I mean, if this is a theta expansion down, so I get lots of strange stuff popping.
The forms go
popping
bigger,
in.
you get more and more ghosts.
So in 8 I get lots of fields. I mean, I get the right ones, but I also get things I don't understand at all. So I can't say anything really.